The purpose of this video lesson is to introduce the concept of measurement and uncertainty and to help teach you how to make proper measurements in science. For this lesson, you will need your new notes packet, your yellow objective packet, a pencil or a pen, and a highlighter. The learning goal that will be mastered during this lesson is 2F, to define uncertainty, explain how it arises, and take measurements so that they reflect the proper uncertainty. Remember, as always with these video lessons, that if things are going by too fast, feel free to pause the lesson and think a little bit about what you're trying to learn. In science, it's very important that we take measurements properly. Our method for taking measurements in chemistry class is going to be to read all the digits that you can from your instrument, and then estimate one more digit. When you're working with a digital instrument, you want to record all the digits on the digital output of your digital instrument. And lastly, remember that regardless of the situation, the final digit of your measurement is an estimate, estimated by you on a non-digital instrument, but the digital instrument itself estimates something into the last position of the measurement. Let's start by looking at 3 rulers. The first thing you have to identify when you're looking at any device to take measurements is you need to identify the smallest marked increment on the device. In the case of this first ruler, I have labels every 1 centimeter, but my smaller increments are these smaller tick lines right here. Each one of those increments represents 0.01 or 0.1 centimeters. The second ruler is identical to the first ruler, so again, each small increment represents 0.1 centimeters. Looking at the bottom ruler, however, these increments are much, much smaller. The big increments on this ruler are only 0.01 centimeters, and so the littlest increment on this ruler ends up being 0.001 centimeters. Knowing the smallest increment tells you how many digits you can have in your measurement. So if I look at this first little stick here, in order to take a proper measurement, I'm going to start by reading all the digits that I know for certain. In this case, I know that the stick is at least 1, but not yet 2 centimeters. Now if I count the little tick marks, I notice that I am past the 6th one, but not yet to the 7th one. The 1 and the 6 represent the 2 digits that I know for certain. Now I need to estimate one more digit. I need to estimate a digit that tells me how close I am to moving toward the 0.7 mark. In this case, I'm barely past the 0.6, so I'm going to estimate that 1. And all good measurements should have units. As I look at the second stick, in this case it looks to me that the stick is exactly at the 3 centimeter mark, but I have to say so very, very carefully. I know for certain that I have at least 3 centimeters. And I can say with certainty that I don't have any tenths. To tell my reader that I believed I was exactly on the 3 centimeter line, I'm going to put my estimated digit as a 0 to indicate that I feel the stick is 3.00 centimeters long. My last stick is measured with a ruler that has much finer increments on it. I know definitively that the stick has made it at least to the 0.01 mark, and as I count little increments, I know that it has made it at least past the 8th little increment. So I know definitely that the stick is somewhere between 0.018 and 0.019 centimeters. And now I need one more digit to estimate how close I am to making it to the 0.19 mark. I think that I'm getting very, very close, and so my final digit I'm going to estimate as an 8. And as always, I add units to my numbers. So as you can see, figuring out the smallest increment on your measuring device is very important, and in every case, your measurement is going to go 1 decimal place beyond your smallest increment. For the first two, my smallest increment was the tenths of a centimeter, and my measurements go to the hundredths of a centimeter. And for my last ruler, my smallest increment went to the 3rd decimal place. My measurement goes to the 4th decimal place. There are 2 ideas that are very important with measurement. Those include precision and accuracy. The more decimal places you have, essentially the better the instrument you are working with, and that's going to lead to greater precision. Precision is reproducibility. Can you get the same answer over and over and over again because there's not much room left for the size of your estimate. Accuracy is a closeness to the true result. A good measurement is both precise and accurate. I find that accuracy and precision are often best thought about in terms of shooting arrows at a target. A person who shoots arrows that's both accurate and precise will hit the bullseye, which is the part that they want to hit, over and over and over again. They're accurate in the sense that they are correct, and precise in the sense that they are reproducible. A person who fires their arrows and they land in the same place every time but not necessarily in the bullseye are precise but not necessarily accurate. And somebody who's just starting with a bow and arrow will often be not accurate and not precise. The arrows will kind of be scattered all over the target. Our goal in science is to create measurements that are both precise and accurate. One important thing about measurements is that no matter how good of a job you do with measurements, the fact that we estimate that final digit leads to all measurements having some uncertainty. Uncertainty is the amount of possible error that's present in a measurement. When you're taking measurements, the uncertainty is assumed to be 10% of the smallest increment, unless it's otherwise noted on the instrument. Let's go back and consider the rulers that we looked at before. We have determined the smallest increments on each one of these rulers. Now I want to go back and determine the uncertainty for each ruler. Since none of the rulers indicate that their uncertainty is anything different than 10% of the smallest increment, we will go with that assumption. So if my smallest increment is the 10th of a centimeter, 10% of that is 1/100th of a centimeter, and so I have an uncertainty of 1/100th of a centimeter on the first ruler and also on the second ruler. The third ruler has much, much smaller increments. They have increments to the nearest thousandth of a centimeter. So my uncertainty here is 10% of that, or the nearest 10,000th of a centimeter. Now I can go back and I can go to my original set of measurements where we thought the stick was 1.61 centimeters long, and I can record a proper measurement that says that this stick is 1.61 plus or minus 0.01 centimeters. What this is actually saying is that we are going to accept the measurement of our stick as being somewhere between 1.60 centimeters up to 1.62 centimeters. Measurements really end up always representing a range of numbers that could possibly be the correct answer. My second stick would then be recorded as 3.00 plus or minus 0.01 centimeters, meaning that my stick has a size between 2.99 up to 3.01 centimeters. Again, my measurement represents a range of possible values for the length of the stick. My final stick has a size of 0.188 plus or minus 0.0001 centimeters. Again, meaning that my stick has sizes ranging somewhere between 0.0187 all the way up through 0.0189 centimeters. So we end up with a range that represents the size of our stick. It is important to make sure when you're done taking measurements that if your uncertainty is in the hundredths place, your measurement ends in the hundredths place. Uncertainty, oops, undo that. My uncertainty is in the hundredths place. My measurement ends in the hundredths place. Here my uncertainty is in the 4th decimal place, so my measurement has to go to 4 decimal places. So when you're done taking measurements, always look back at your measurements and your uncertainties and make sure that your measurement and your uncertainty end in the same decimal place. When taking volume measurements, we have to be a little bit careful of where we put our eyes. It's always important when looking at a liquid to read at the bottom of the meniscus. The meniscus is the little curved area that you see at the top of the liquid. And it's also important to keep your eyes at the meniscus level. So you need to put your eyes on level with your instrument and get down very, very close. Failure to do this will lead to something we call a parallax error. If you are looking down on your instrument, the volume reading that you're going to get is going to be too low. If you're looking up at the meniscus, the volume reading you're going to get is going to be too high. You will only get an accurate measurement by putting your eyes in line with the bottom of the meniscus. So here we have some pictures of some graduated cylinders. This first graduated cylinder is marked at 8 milliliters and 9 milliliters and has 10 little tick marks in between. So here's a situation where my volume smallest increment is 0.1 milliliters. My uncertainty is 10% of that, or 0.01 milliliters. Now I want to take my measurement. I know for certain that the meniscus is above the 8, but not yet to the 9, and I know for certain that it's 0.1, 0.2, 0.3, so I know 8.3, but not yet 8.4, and I'm going to estimate how far I am between the 8.3 and the 8.4. I think I'm a little past halfway, so I'm going to say that my measurement is 8.36 plus or minus 0.01 milliliters, which means that I believe my volume to be somewhere between 8.35 and 8.37 milliliters. Here's a different graduated cylinder. This one has numbers at 40 and 50 milliliters, which must mean that the individual volume markings in between, the tiniest little increments, in this case must represent 1 milliliter. 10% of that is an uncertainty of 0.1 milliliters. And as I look at the bottom of my meniscus, I know that I am past 40, but not yet 50, so I know the 4 for certain. Here's 41, 42, 43. And it looks to me that my meniscus is exactly on the 43 mark. Knowing that my measurement and my uncertainty have to end at the same place, I'm going to have to write 43 so that it goes to the tenths place. I'll do that by writing it as 43.0 plus or minus 0.1 milliliters. Notice that that meets the requirement that my uncertainty and my measurement end at the same place. That means that I believe my volume to be somewhere between 42.9 and 43.1 milliliters. Lastly, let's talk about the 10 milliliter graduated cylinders. Our 10 milliliter graduated cylinders have increments marked at every 0.2 milliliters, just like this one here. Here's a 3 milliliter mark, here's a 4 milliliter mark, but the increments represent 3.2, 3.4, 3.6, 3.8, and 4.0 milliliters. One of the rules about our measurements is that the measurement always has to be a multiple of the uncertainty. So if we have 0.2 milliliter increments, possible measurements are going to have to be things that end in even numbers. So things like 1.00, 1.02, 1.04. So as I look at my little graduated cylinder, I've identified that my increments are every 0.2 milliliters. 10% of that is 0.02 milliliters. And now I know that I need to read my measurement all the way out to the second decimal place, and that I need to end in the second decimal place with something that's a multiple of 0.02. So my measurement here, I know it's past the 3, past the 3.2, past the 3.4, and on its way to 3.6. It looks to me that we aren't quite halfway between 3.4 and 3.6, so I'm going to estimate that we're at 3.48 plus or minus 0.02 milliliters. That's going to leave me with a measurement that is somewhere between 3.46 all the way up to 3.50 milliliters as I take into account the uncertainty of my device. Again, I've met the criteria that my uncertainty is in the second decimal position and my measurement goes to the second decimal position. Hopefully now you'll be able to define uncertainty, explain how it arises, and take measurements so that they reflect the appropriate uncertainty. Bring your notes packet with you to class tomorrow, and we'll be doing some measurement practice in class.